So, in the last class, we have talked about the Kane Mele model, but I have gone a little fast there in order to finish up the calculation of the Z2 invariant, which we have done it quite extensively. So, right now we'll rerun some of the discussions that we already had and talk about the model a little more and show some of the results that we can get from the model. Okay. So, we start with this again with the Kane Mele Hamiltonian. I've already told that there are certain features that are distinct from the Haldan model, and we'll again come to that in just a while. So, the first term is the tight binding term, which is there in graphene. This is really the Haldan term, and I have said this that you can use either a T2 or a lambda SO there. Mostly in literature it's used as lambda SO, so I have written it as lambda SO, and this is the Semenov term, which opens up a gap of trivial nature at the Dirac points. Okay. So, it's a simple model which is two copies of the Haldan model, and that's why it's written as Haldan square, and it conserves the SZ component or Z component of the spin, angular momentum, and I have written it with a capital SZ, but sometimes in literature it's written with a small sz. So, here SZ denotes the Z component of the true spin or the actual electronic spin. So, this has been told that the spin up, the upspin particles which correspond to a Haldan model with a flux phi equal to pi by 2. You remember the flux comes from these the second neighbor hopping, which is exponential I phi, and then of course one has a Ci dagger Cj. Now, this is second neighbor, so we write it with a Ij, or you can write it just in case you are not comfortable with Ij, because that's used for the nearest neighbor as we have done it for the first term. You can use a Ik also. So, instead of a j, one can use a k, just to make sure that that's the next nearest neighbor and not the nearest neighbor. We have shown this picture many times, and similarly for the spin down electrons, it's another Haldan model, and with this flux equal to minus pi by 2. So, there is a flux pi by 2 for the upspin and minus pi by 2 for the downspin, and this is exactly what is written here. And it takes a block diagonal term where the upper block on the left is for the upspin and for the lower block downspin, each one of them, each of h up and h down, like a 2 by 2 Hamiltonian of the Dirac form. What I mean by Dirac form is that it can be written as d dot sigma. Okay. And the Hamiltonian has time reversal symmetry now, which we have discussed elaborately. Okay. Now, there is another term that's added which is called as a Rashba spin orbit coupling. We'll do a little discussion on that in just a while, and the term is written as I lambda r, and there is a Ci dagger, and these sigma cross Dij will tell you what Dij is. Dij is actually a unit vector that connects to the site from site I to a nearest neighbor site j, and of course, the rest of the things are all same. Now, this creates one additional complication, which is what we have seen here. The Hamiltonian no longer remains as block diagonal, as you can see here. Okay. There are off diagonal elements in this 4 by 4 Hamiltonian that arise, and it does not have this block structure that you see here. Okay. Now, how do I get this term, and how this thing comes into picture is what we will see. And so, some of the results are same with and without the Rashba spin orbit coupling, though they are quantitatively different, and will have large application in terms of spintronics if we apply or rather include this term. And as I said earlier, this term is quite possible in a perfectly two-dimensional system which our graphene is, because there is an inversion symmetry breaking happening there, which will give rise to an electric field, and this the spin will couple to the electric field and so on. Okay, we will just come to that in just a while. And we get spin filtered 8 states because of this term that we see here, and there are these spin currents that will be there, and one gets a quantum spin Hall phase which is observed in the system, and there is a quantized Hall conductance in the spin sector, which we call it as quantum spin Hall conductance, as opposed to the charge Hall conductance, which is equal to 0 here. It is 0 because the system has time reversal symmetry, and we have shown that how the system has time reversal symmetry earlier. So the spin Hall conductance is quantized at a value which is E over 2 pi. Let me try to derive this term that you see here, the lambda r term, and this is like how this sigma cross dij and the z component of that come is what is important. I mean, you have to take a note of this z component because we are writing a Hamiltonian whose eigenvalues will give energies. So it cannot be just a vector. So it will have a scalar, and that z component makes it a scalar. Okay. So we write down the wave function in the Wannier basis. Okay. And the wave function is of this form, where these Ci's are the operators and these W's are the Wannier wave functions, and the Wannier functions are localized at some sites which are given by this Ri. These obey the orthonormality condition which is given by this equation. So let us call this as equation 1 and this as equation 2. So it is clear that it's W star, which is a Wannier function, Ri minus R and the Rj minus R, where I and J are different sites, will be equal to 0, and if I and J are same, then that will lead to the normalization of the Wannier functions. Okay. Now this is well known that when you want to write derivatives on a lattice, one does it like this, that so it's f prime of x is equal to f of x plus h minus f of x divided by h, and limit h tends to 0. That is a definition that we have learned probably in school. So there is these Wannier functions which are written at Ri plus D site, where D is the nearest neighbor site, and taken subtracted the Wannier function at the ith site, and then because it's a gradient, so it should have a direction. So this is that a d cap direction that is shown, and divided by the d, which is the length of the nearest neighbor vector, okay, or the distance, nearest neighbor distance. So because gradient is a vector, so this d cap, which is in the direction connecting the two sites Ri and Ri plus d, that is shown here. So this is the definition of momentum or a gradient of a scalar function. Now why is that required? That is required because we need to write down the momentum, the operation of the momentum on the wave function, and this momentum is written as minus I h cross del del x. So for del del x there is a shorthand notation which is del of x, and we have taken h cross equal to 1 without any loss of generality, and this is equal to a Ci and a Wri, where Ci is an operator at the site I, and that is the Wannier function. So this can be written as minus I, and then now you apply the gradient operator just from this equation 3. Let us call that as equation 4. So we apply the same thing. So del del x is nothing but say something like a gradient vector, and this gradient is written as x cap dot the gradient of W at Ri. Now this we already know from 3, and that can be expanded. Now since we have a x cap here, you can write it as x cap as well. So this is equal to dx by d square and so on. Okay. So, that is exactly what we have done. Now, this is no longer a vector, this quantity, because you have dotted with a x cap direction, and this x cap comes because we have taken a px, it will be py will get a y cap here. So, what we land up with is an operator and then this dx over d square and these the linear functions at the, or the difference between the linear functions at the consecutive or the nearest neighbor sites. So, we are ultimately interested in a quantity like this, which is psi dagger px psi, and that is because that would be there in this kind of a term. So, we are sort of trying to get that here. Now, ultimately this will be related to the form that we just got, and then we write down, if you look at it carefully, it is pretty easy. So, this is that Ci dagger Cj coming from, the dagger is coming from psi dagger, and Cj is coming from psi, and then the px operator is written here exactly in the same way that we have done it in equation 4. Let us call this as equation 5. So, now because of the orthonormality condition, that is this and this will only survive provided d connects to the nearest neighbor, and this with this will give you a 0, because that is the orthonormality coming if I is not equal to j, and of course I is not equal to j. So, this left hand side that we have in equation 5 has a form which is nothing but this 6, where this w star ri and w rj plus d will give you 1 because of the normalization where d connects to the neighboring sites and so on. So, this is a Ci dagger Cj and then the dx by d square, and the volume integral over r goes on to make up for the orthonormality condition. Okay. And similarly for Py, one gets this exactly the same. Let us write it as 7, and then we have a dx over d square and a dy over d square, and so this is px and py that one gets here. Okay. And of course, you do not see any px and py here, but then we will show that this is really coming out from a term like that. Okay. So, this is 6 and 7 make up for the two equations that we need for these the expectation values of px and py. Now, this that the Rashba term is written as sigma x py minus sigma y px. Okay. This is basically the sigma cross p and the z component of that, or you dot it with a z. Okay. And this z is nothing but we will tell you in a moment that it is nothing but the electric field direction of the electric field which occurs, or rather which arises because of there is a gradient of the crystal potential. Okay. So, now with all these things we have there is this dagger that is missed here. So, psi dagger and so on, this sigma x py minus sigma y px, which is nothing but sigma cross p, the z component of that, and a psi r. So, we get a Ci dagger and a Cj coming out from this, and then a sigma x dy minus a sigma y dx exactly coming out from this, and there is of course a d square that comes out. Okay. And there is a I factor there, and this gamma is simply nothing but either you call it a lambda r or something, but lambda r we are going to get it here. So, sort of wrote a constant, a coefficient of this Rashba term, and this is nothing but what we want. Okay. So, the Rashba term indeed has a form. So, this one is what you start with, and then you end up with a term that is like this, and this is exactly what is written here. Okay. This one needed a little bit of hand holding in order to derive this form, but I sort of wanted not to break the flow in calculation of the Z2 invariant, which is why I skipped it there, but now you have it here. Okay. And this has already been shown that in the momentum space the Hamiltonian is written as this. Now, we of course do not have a block form. This is a block here, this is a block here. but the blocks are being mixed by these off diagonal forms which are written in terms of rho k, and the rho k, if you look at it here, it is purely coming out from the Rashba term. Okay, and this is a little lengthy derivation, but one should be able to do it without much problem, because one just needs to Fourier transform each one of the terms that we have written in the Hamiltonian that we have written here. Okay, so this Hamiltonian, so this is the most important equation, and let's call it as a capital 1. Okay, and so this is by Fourier transforming equation at capital 1. Okay, and the various other things which are there written here, which is xi k or some this is that thing that is coming out here, that's here, and the gamma k is also there, which are part of the this is that nothing but the T2, the Holden term. So it's a spinful Holden term here, and the kinetic energy term which is there in graphene is the tight binding kinetic energy that is given by the xi k, gamma k and rho k, and this is the 4/4 Hamiltonian. You remember the Holden model was 2/2 because the spin wasn't taken into account, it was only the sublattice degrees of freedom, and here of course we have taken into account spin, and that's why the size of the Hamiltonian now have gone up, and it has become 4/4. And these are some of the band structure plots of these. So once when some diagonalizes this Hamiltonian, which can be done in a computer, and then one get for various parameters. Now you see that we have shown it explicitly for a few parameters which are given by lambda r equal to 0, lambda v equal to 0, which means it's only the graphene thing and there is no lambda r or lambda v. And then one has sort of touching Dirac points here, and once when one switches on a lambda r, then there is the band still touch, but the conduction band and the valence band, they become spin resolved. So the ones that you're seeing in blue and red are spin resolved valence bands, and these pink or something magenta and the green, they correspond to the conduction bands, spin resolved conduction bands. When you put lambda v equal to 0 but lambda r not equal to 0, a trivial gap opens up at the Dirac points, which is a known result. Now if you have both not equal to 0, that's the Rashba term as well as the Semenov term not equal to 0, there is a gap as well as the spin split bands can be seen. Okay, this is exactly what is written there. So these are numerical calculations that are emerging out from this dispersion or this Hamiltonian that comes out here. Okay, let me do a little discussion on the Rashba term. Okay. A brief discussion has already been done. This is little more to supplement that and so on. So when you have a charged particle with a velocity v, moving with a velocity v in a region where there is a magnetic field B, there is a Lorentz force on the charged particle. So the Lorentz force is given by FL, and which is equal to a minus VE V cross B. So V is the velocity and B is the magnetic field, and because it also has spin, which is now we have to necessarily include spin in our discussion, there is also a Zeeman energy which is given by, let's call it a Ez, and which is equal to a mu B sigma dot B. Okay, there is of course one is force, the other is energy. So this is what we are writing, and then mu B is called as a Bohr magneton, which has a value 9.27 into 10 to the power minus 24 joule per Tesla. Okay, so Now, when the electron is subjected to an electric field, then in the rest frame of the electron, it experiences a magnetic field. So, let me write that. In its rest frame, it experiences an effective magnetic field. A B effective, which is given by minus E cross V divided by c square, where c is the speed of light. This is electrodynamics. You can check Griffith's book. So, that is the effective magnetic field that it experiences, and this gives you a net a Zeeman energy, which is given by mu b E cross V divided by c square dot sigma. So, it is b dot sigma or sigma dot b, does not matter. I mean, you can write it. So, this is the, so it is sigma dot b, which is nothing but, so this is like mu b sigma dot b effective, and b effective appears just on this tape above. So, this Ez prime is nothing but the spin orbit coupling term, and we can write down, if we write it down in terms of operators, then this spin orbit term is written as mu b over mc square E cross, now I make this V as P divided by M, and this is written as mc square, and there is a sigma dot there. Okay. So, this is the spin orbit coupling term that we are interested in, and you will see that the Rashba term looks very similar to that. And what is the origin of E in crystal lattice? So, E is originated by the crystal potential, which is given by minus E equal to minus gradient of V, where V is the crystal potential. Which is present due to the presence of ionic crystals or ionic sites and so on. Now, what happens is that if you have a purely two-dimensional sample, which our graphene is, then your E becomes in the direction of z cap. Okay. So, it is in the direction of z cap. This yields a form for the HSO as say we write it with a alpha r by H cross, and then there is a z cap across P dot sigma. I have changed the order of this E, and which I have been doing it. So, sigma dot this term or this term dot sigma, it really does not matter. So, this is z cap cross P dot sigma, and then all these other things like mc square etc., they are being absorbed here. So, alpha r by H is it replaces this mu b Ez divided by mc square, which are scalar quantities. Okay. So, the spin orbit coupling takes this form, which is z cap is the direction unit vector in the z direction, which is perpendicular to the 2D plane, and this is crossed with the momentum and dotted with the electronic spin. So, here make no mistake that we are really talking about spin by sigma. Usually when we write a graphene Hamiltonian, we denote sigma to represent the sublattice degrees of freedom, but this is real spin. Okay. So there are this alpha r is actually measurable and can also be enhanced by using gate voltage and various kinds of other things, such as heavy adder terms like gold etc. in a graphene matrix, but I will not go into details of that. So, typical values of alpha r in these LA, ALO3, these are interface of these heterostructures SRTIO3, etc. This has a value, it's about 0.5 to 0.6 into 10 to the power minus 11 EVM. Whereas for some of the topological insulators, alpha is typically 1 or 2 orders of magnitude large, and it can have a value which is 10 to the power minus 10 EV meter, and this can be further enhanced by using external means. Will not go into that, but how is this relevant for us, why we are talking about it, why we want to include an additional term. As I said, that this additional term obeys the time reversal symmetry, or rather all the symmetries that graphene has. So if we add a term which does not violate any of the parent symmetries of graphene, then it might as well be there. Okay. It unfortunately turns out that the magnitude of the spin orbit coupling, or that alpha r, or the strength of the spin orbit coupling in graphene, is quite small. It's of the order of a few MeV. However, it is still has a fundamental importance in this study of quantum spin Hall insulators and the study of spintronics, which could be, you know, next generation devices for with replacing the electronic devices, for a number of reasons which I do not want to elaborate here, but one of them is that the spins do not undergo Joule heating, it is not scattered by impurities and so on, and hence they could be, you know, potential candidates for doing device making. Okay, spintronic device making. So what happens is that in presence of the spin Rashba term, the velocity of the electrons becomes spin dependent, and they are given by, so this velocity, and I write it with a subscript sigma because now it means that it's a spin dependent velocity, which means that the upspin electrons will have a different velocity than the downspin electron. This was not the case earlier, where the Hamiltonian, etc., everything was spin independent, as if we are talking about spin polarized, that is, spin doesn't enter into the discussion. Now that's not the case. So this is equal to, it's proportional to say a del k of this Rashba term. Let's write it, okay, right, we're writing it with the SO. So let me write it with the SO, and this is nothing but this is equal to some alpha r z cap cross sigma. And now you see that why I wrote it with V sigma, because there's a sigma there, and so on. And this will give you different velocities to different spin components, that is upspin and downspin component. So it's pretty much like, you know, the Magnus force that one sees in a classical spinning object, where there is an effective force on that, there is a, and that in this particular case would make these ups and downspin electron separate their ways in terms of you know, when they move in a system, they'll sort of go in different directions, and that will create a spin current or spin polarized current, which depends on spin. So there will be upspin and downspin will be segregated, and also will give rise to a spin sort of voltage, and this is called as a spin Hall voltage, because it's not in the direction of the current or the electric field, is perpendicular to that. And one has, what I'm trying to say is that, so here you'll have upspin, say for example, and you'll have downspin there, and so there is a spin Hall voltage. So if you calculate a voltage between this and so on, so this, there'll be a spin Hall voltage, and this spin Hall voltage can be, if it's the magnitude is considerable, it can contribute to spintronics. Okay, So, let me do a comparison between the Halden model, or what we call as a Chern insulator, and this quantum spin Hall insulator. So, we will call a Chern insulator or same as Halden model, and quantum spin Hall insulator, QSH insulator, and or a same as Kane Mele model. Okay. So, let me make a comparison between the two in terms of a number of things that we have learned so far. It's like a summary of what we have learned. So, we have in no particular order. So, there are chiral edge states, that is electrons move in different directions in opposite sides of the sample, and there are helical edge states where they are spin filtered. So, this is one. So, this spin filtered second is this is called as a Chern number as the topological invariant, and that is why they are called as Chern insulator. Z2 invariant. Okay. Number 3, time reversal symmetry is broken. Which let us call it as TRS is broken, TRS is intact. So, we have told about the implications of time reversal symmetry. So, it shows quantum anomalous Hall effect. Shows spin Hall effect. We will show you the spin conductivity or the spin Hall conductance, spin Hall effect, quantum spin Hall effect. Write it. Quantum spin Hall effect, and one sees a plateau in the spin Hall conductivity at E square over H, plateau at E over 2 pi. Last but not the least, of course, we have a low energy Hamiltonian. H equal to H cross Vf Qx sigma x tau z plus a Qy sigma y plus 3 root 3 T2, which you can call it either a lambda SO also, sigma z tau z, and similarly a low energy Hamiltonian is H cross Vf Qx sigma x tau z plus a Qy sigma y, and a plus this 3 root 3 T2 sigma z tau z sz, that is the spin, and a plus a lambda r and a sigma x sy tau z minus sigma y sx. Compared to the last slide, we had to change these notations a little, because now sigma denotes the sublattice degrees of freedom, while S denotes the actual spin degrees of freedom. Okay. So, these are a summary of these two type of insulator, and both are very important in their own right. Okay. So, here we just show that the graphene only with Rashba term, there is no Holden term and so on. So, you see that this is just the tight binding graphene and this is the Rashba term. So, you see that there are this semi-Dirac or semi-metallic nature, not semi-Dirac, semi-metallic nature at the K and the K prime points, which also that there is a band touching, because without a sigma V or the Holden term there will be no lifting of gap, but now you see the spin resolved bands. Okay. So, it is a gapless scenario, there is no gap there even with lambda r not equal to 0, and you have we have just done a Fourier transform of this and then have plotted this, or rather solved this model and plotted this dispersion. Okay. So, finally, the spin Hall conductivity, which is obtained using, so this is the spin Hall conductivity with you can call it a S also, but it is written with a Z, because you are talking about the Z component of the velocity. So, this is really the spin Hall, not the charge Hall conductivity, which is equal to 0 anyway. So, this is equal to this, this is the Fermi function, which is not important, because if you are talking about 0 temperature, then this is equal to 1, and this is the Berry curvature, and the Berry curvature can be calculated using this formula, which is very similar to what you have seen for the Kubo formula, and the velocities are calculated from this gradient of the Hamiltonian with respect to kx and ky, or you differentiate. So, for Vx you take a del kx, and for Vy take a del ky. The only thing that is important is that now these is the velocity operator, but that is not what is used here. You use Vsi and the z component, which requires one to calculate the anti-commutation relation of these quantities. So, it is a, if you want Vsx then you take a Vx and then h cross by 2 as z sigma 0. Sigma 0 is simply E over 2 pi. This is just the scale of the conductance. Okay. So, one does this calculation and of the Berry curvature and then put it into the expression for spin Hall conductivity. Let us call it as 1 and 2. So, one calculates 2 and then put it into 1, put Fermi function equal to 1 at t equal to 0, and then you calculate this spin Hall conductance, and the spin Hall conductance comes out to be very nice, a form which is it is 0 in the vicinity of the Fermi energy. So, this is the bias voltage. So, you are biasing the system, and this bias voltage changes the Fermi energy, because the electron occupancy is altered as you bias it, and you see that there is a very broad plateau in the vicinity of EF equal to 0 or 0 bias, and it's very symmetric and so on. So, this is E over 2 pi that exists for certain range of values of the EF or the bias voltage, and when EF lies in the gapped region of the dispersion spectrum. So, when EF lies here, which is what we have shown earlier, if EF, say for example, were both are non-zero. So, when the EF lies in this gap and not inside the band, then this is it gives you a plateau, and then as the plateau sort of goes away, and the spin Hall conductance becomes dispersive, or it sort of rises when the Fermi energy is such that it falls within one of the conduction or the valence band. This is exactly the feature that we have seen earlier. Okay. And so, in this, so if lambda r and lambda v are taken from the region outside, that is this white region here or here or here or here, then of course the Z2 invariant vanishes, and the plateau structure vanishes as well. Okay. So, this is by and large what one gets from the Kane Mele model, and the explicit calculations of all the quantities that are of importance are presented here. Okay. So, these are the helical edge modes that we have shown earlier, but is presented once again. So, these P, Q, R and S are these things here. So, this is a topological insulator, that is a quantum spin Hall insulator. So, let me write it as QSH insulator, and this is trivial insulator with no edge modes. So here you are inside the blue region here, the light blue region, that is sky blue region inside, and for the right panel you are outside. Okay, this is what completes the discussion on the Kane Mele model. Let me sort of do a sort of summary slide for the quantum spin Hall phase, the mercury telluride and the cadmium telluride quantum wells, and the Kane Mele model, just setting up a connection between them. These are some of the people who have contributed immensely on this topic of quantum spin Hall insulators. And once when the Kane Mele had proposed this model, somebody has done an experiment, and the person who did that experiment is Molenkamp, and the theory had been almost immediately proposed by Zhang. So Molenkamp. This is Taylor Hughes, and this is Bernevik. So these people, and later on many other people, have contributed immensely to the development of the field. So what happens is that so there are these 2,6 materials, which are these semiconductors rather. So there are these 2,6 semiconductors which are important because these semiconductors have sp hybridization, and along with these have a zinc blend structure. Okay, and so they actually belong to this 12 and 16 columns of these periodic table, and you see that there are zinc and cadmium and mercury. This is what one of the things that are important. I mean, these two are important in this particular context, this cadmium and mercury, and this either selenium or tellurium. This is important, and so on, and then this is what exactly we want to the heterostructures to form, or the quantum wells to form with this. So this is that thing a little blown up. There are these so cadmium and mercury, and then there's this thing that are important, and so on. As I said, that there's sp hybridization, so as opposed to the other the transition metal dichalcogenides, Bi2, Se3, etc., where only one orbital is near the Fermi level. There are two orbitals involved in the in making up the energy levels close to the Fermi level. And even though this has been discussed, I mean, in the sense that this is this gamma is actually the high symmetry point in the Brillouin zone, and this gamma is subscripted with these 6, 7 and 8. You see that there is a 6 here, there is a 7 here, and there is a 8 here. So the 7 and 8 are split by the spin orbit coupling, which is present in this material. In general, this gamma 6 is in the conduction band and gamma 8 is in the valence band, which is what you see. So this is the conduction band in CDT. This is the conduction band, and this is the valence band, and which is the conduction band is of course above the valence band, and these gamma 7, even though they are spin split, but they are this gamma 7 is not under consideration because it's far away from the Fermi energy. Very interestingly, the mercury telluride HGT has an inverted structure, which is what has been told, and here of course the gamma 6 comes below the gamma 8, and this is what creates all the interesting thing, which is what these people who I had shown in the earlier slide, they have understood. And this is a closer picture and so on, and you see that there is a gamma 6 in the, this is HGT. and a gamma 8 is up there. So the red line is actually the Fermi energy, and you see that this gamma 6 and gamma 8 have an energy which is minus 0.3 electron volt, or about 300 milli electron volt. Okay. So this is interesting, and when you make a structure out of it, when you make a a sort of sandwich the mercury telluride in between two cadmium telluride slabs, when the mercury telluride starts dominating the phase diagram or dominating the physics, that's when there is a interesting thing happens. And this interesting thing is shown here in the lower panel. For D less than DC, you see that there are these blue is the conduction band, and this is a valence band, and so on, and this is the HGTs inside, and there are these CDTs outside. So the electron and the hole bands are shown by blue and red colors, and so on. And when the width of the well, it is increased, so this way you increase the width of the well, and when it happens, then D greater than DC, one has an inversion of the, so the electronic level comes below the hole, and that's where, so this is a trivial insulator, and this is a topological insulator, so topological, and in particular if we talk about it, it is a QSH phase that emerges. Now there are a few inputs that one can get from this. For a given thickness D, DC, which is equal to I believe this is the value. So what happens is that the electron and the hole bands they become degenerate. So this one, so E1 and H1 they merge. So this basically is shown one electron band and hole band. The cartoon picture is it's good enough to only show one, and they merge and then they switch order. Okay, and when they merge, that's called as the degenerate point. And this can be exploited in the following sense. Okay, so at this thickness, the E1 and the H1 will merge. It's less than DC. If it is less than DC, then E1 will be higher than H1, and if D is greater than DC, then E1 will lie lower than H1. So that tells you that if you think in terms of a Dirac type of Hamiltonian, this is like a D dot sigma, then the dz, which is the mass term, okay. So this dz is less than 0 for HGTE, which means it's negative, that's why the inverted band structure comes, and dz greater than 0 for CDTE. Okay. So at the degenerate point, dz is equal to 0. Okay. So where one sees the gapless Dirac fermions, at the interface. Okay. So based on this, BHZ wrote down a Hamiltonian. And this is what we have seen. that 4 by 4 Hamiltonian, and which of course has a block diagonal nature comprising of the gamma 6 and the gamma 8 levels, which are connected by time reversal symmetry, because this has time reversal symmetry. So, they are basically the Kramer's pairs and the spin split Kramer's pairs. Okay. And so, in the same spirit, the Kane Mele Hamiltonian is also block diagonal without the Rashba term, and that gives rise to a spin Hall, quantum spin Hall phase. So, there is a connection between this and the Kane Mele Hamiltonian, which also is block diagonal in the spin space, and one can calculate, and that is what we have shown here.